Hello, science fans! Bill Nye here, ready to dive into the fascinating world that surrounds us. Motion is happening all around us, all the time. It's a constant dance of energy and change that shapes our experiences. From the grandest scales to the tiniest particles, movement is the key. Think about it. When you get out of bed, see a car zoom by, its engine roaring as it races down the street, or watch a bird fly, gracefully soaring through the air with effortless ease. Even when you feel still, completely at rest, Earth is spinning and orbiting the sun, a cosmic ballet that never stops, so you're always moving through space, hurtling through the cosmos at incredible speeds. Science helps us see the hidden motion in everything, revealing the dynamic nature of reality. From tiny particles, atoms and molecules vibrating and colliding, to galaxies, vast collections of stars swirling in the depths of space. Motion is fundamental to understanding the universe and is the starting point for physics, the science that explains how the world works. Physics explains how things work, providing the tools to analyze and predict movement, from bouncing balls, obeying the laws of gravity and elasticity, to shining stars, powered by nuclear fusion and radiating light across vast distances. To understand it, we need to describe, measure, and predict, using careful observation and precise calculations, how things move. Today, we'll explore how to know if something is moving, how to detect and analyze its change in position, how to measure its journey, quantifying the distance it covers and the path it takes, and how to describe its speed and direction, understanding its velocity and trajectory. By the end, you'll be able to look at a moving car or a flying bird, observing their motion with a scientific eye and say, I know the physics behind that. You'll unlock the secrets of their movement. Get ready for an exciting ride into the world of motion. It's going to be a blast. Let's get into motion. So, what exactly do we mean by motion in the world of science? It's a fundamental concept, but it's also surprisingly nuanced. We use the word motion all the time in our daily lives, but in physics, it has a very specific meaning. Let's break it down and explore what motion truly entails. At its core, an object is considered to be in motion if its position changes over time. This seems simple enough, right? But let's dig a little deeper. Imagine something is right here, at a specific location now. And then, a little while later, it's over there, in a different spot. Clearly, it has moved. It has undergone motion. But here's a crucial question. How do we definitively know that its position has actually changed? What's our basis for comparison? The answer lies in comparing it to something else, a fixed point, a stable object, what we call a reference point. This reference point is key to understanding motion. To illustrate this, imagine you're sitting comfortably in a car, and beside you in the next lane is another car, keeping pace, moving at approximately the same speed as you are. If you focus solely on the other car, it might seem like you're both perfectly still relative to each other. However, if you shift your gaze to a tree standing firmly on the side of the road, you instantly realize that you're both moving rapidly. This simple example highlights a fundamental principle. Motion is always described in relation to something else. It's not absolute, it's relative. And this, in essence, is the concept of relativity. The way we perceive an object's motion is entirely dependent on the observer's point of view, also known as their frame of reference. Think about a passenger comfortably seated on a train. To them, the person sitting directly across the aisle appears to be perfectly still. But to someone standing on the train platform as the train whizzes by, both passengers are hurtling along at a considerable speed. So who is correct in their observation? The answer is both. The key is that it all depends on the chosen reference point. Therefore, motion can be defined as a change in position that occurs over a period of time, and this change is judged by an observer who is using a specific reference point to make their assessment. So, it's not simply about an object moving, but rather about how that object is moving in relation to something else that we consider to be stationary. Before we can accurately measure how far something has traveled or how fast it's going, it's absolutely essential that we first agree on what we're using as our basis for comparison, our reference. Without a clearly defined reference point, a fixed marker in space, the question, is it moving, becomes fundamentally ambiguous and has no definitive answer. Science at its heart is about striving for precision and clarity, so it's crucial to always carefully consider and define the reference point you're using. With this understanding of relative motion firmly in place, let's keep that important concept in mind as we continue to move forward and explore more fascinating aspects of physics. Let's dig deeper into reference points. They're essential for describing motion. A reference point is a place or object used for comparison to determine if something is in motion. Usually, we pick something we consider stationary, like a tree or a building. Imagine tossing a ball on a spinning merry-go-round. To you, the ball moves straight. To someone on the ground, it follows a curved path. The same event looks different depending on the reference point. That's why choosing a reference point is the first step in describing motion. In most physics problems, we use Earth's surface as our reference point for simplicity. But remember, the ground isn't truly stationary, it's just convenient. Whenever you say something moved, always ask, moved relative to what? That question unlocks the secrets of motion. Reference points shape our understanding of every journey. Smart scientists never forget to define them. Now, let's measure motion starting with distance. Distance is the total length of the path an object travels, no matter how twisty or winding. Think of a car's odometer. It adds up every meter you travel, even if you drive in circles. Imagine an ant walking 5 centimeters east, 3 north, then 5 west. Add each segment. 5 plus 3 plus 5 equals 13 centimeters. Distance only cares about the total path, not direction. It's a scalar quantity, just a number, like 10 meters or 50 miles. Other scalars include time, temperature, and mass. The standard unit for distance is the meter, but we use kilometers or centimeters as needed. In a 400-meter race, you run 400 meters even if you end up where you started. Distance is your journey's total length, like your personal odometer. It's a simple, useful way to start thinking about motion. Remember, distance measures the path, not the direction. That's the first step in tracking any journey. Distance tells us the total path, but sometimes we need a more direct measure: displacement. Displacement is the shortest straight-line distance from start to finish, including direction. It doesn't care about the winding route, just where you started and ended. Back to our ant, it walked 5 east, 3 north, 5 west. Its displacement, just 3 centimeters north. Distance was 13 centimeters. Displacement is 3 centimeters north. Displacement is a vector. It has both magnitude and direction. Other vectors include force and velocity. Vectors give a more complete picture of motion. In a 400-meter race, you run 400 meters, but if you end where you started, your displacement is 0. You can move a great distance but have 0 displacement. Understanding the difference between distance and displacement is key. Displacement tells you how far out of place you are from where you began. It's a crucial concept for mastering motion. Always ask how far and in which direction. Now, let's talk about how objects move, starting with uniform motion. Uniform motion means traveling equal distances in equal intervals of time, constant speed in a straight line. Imagine a toy train covering 1 meter every second, predictable and steady. Real-world examples include a cruise ship sailing straight at constant speed. Perfect uniform motion is rare cars, and people usually speed up or slow down. But uniform motion is a key building block in physics. On a distance-time graph, uniform motion is a straight, upward-sloping line. The steeper the slope, the faster the object. As long as the line is straight, the motion is uniform. It's a simple, powerful way to visualize steady motion. Uniform motion helps us understand more complex movement. It's the baseline for studying how things move. Most real-world motion is non-uniform. Objects travel unequal distances in equal time intervals. This means speed is changing, speeding up, slowing down, or both. Think of a city bus. It starts, accelerates, cruises, slows, and stops, covering different distances each second. Walking through a crowded hallway or a leaf fluttering to the ground are also non-uniform motion. Anytime you start, stop, or change pace, you're experiencing non-uniform motion. On a distance-time graph, non-uniform motion is a curved line. If the object speeds up, the curve gets steeper. If it slows down, the curve flattens. The shape of the curve tells the story of how motion changes. Scientists use these curves to analyze motion in detail. Non-uniform motion makes the world dynamic and interesting. It's the reality behind every stop-and-go journey. Understanding it helps us predict and describe real-life movement. Non-uniform motion is everywhere. Just look around. It's the adventure in every trip. Now let's put distance and time together. We've explored each of these concepts individually, understanding how to measure them accurately. But the real magic happens when we combine them. To measure speed, how fast something moves. Speed is all about that relationship, that dance between how far something travels and how long it takes to get there. It's a fundamental concept that governs so much of our physical world. Speed is the rate at which an object covers distance. Think of it as the pace of movement, the swiftness of progress. It's not just about getting from point A to point B, but how quickly you make that journey. The formula is simple. Speed equals distance divided by time. It's a straightforward equation, but it unlocks a powerful way to understand motion. By knowing the distance traveled and the time it took, we can precisely calculate the speed. If you bike 20 kilometers in 2 hours, your speed is 10 kilometers per hour. This gives you an idea of how quickly you are progressing on your cycling journey. Speed's units are always distance over time, meters per second or kilometers per hour. These units help us standardize how we measure and communicate speed, ensuring clarity and consistency. Speed is a scalar. It only tells you how fast, not the direction. It's purely a magnitude, a numerical value representing the rate of movement. A car's speedometer shows speed, not direction. It indicates how quickly the car is moving, but not whether it's heading north, south, east, or west. Two cars at 60 kilometers per h, one north and one south, have the same speed. Their rate of movement is identical, even though their paths diverge. Usually we calculate average speed for a whole journey, especially with non-uniform motion. This is because speed isn't always constant. On a bike ride, you might go faster downhill and slower uphill, but your average speed summarizes the trip. It smooths out the variations and gives you a general sense of your pace. Average speed is a useful way to describe overall motion. It gives us a single number to compare different journeys, whether it's a short commute or a cross-country road trip. Speed helps us quantify motion in everyday life, from the pace of our walk to the velocity of a speeding car. It's the foundation for understanding how fast things move. It's a key building block in physics and our understanding of the world. Remember, speed is distance over time, simple but powerful. It's a fundamental concept that helps us make sense of the world around us. Let's see how direction changes the story. Because while speed is important, it's only half the picture. If speed is how fast, velocity is how fast and which way. Velocity is speed in a specific direction, a vector quantity. The formula velocity equals displacement divided by time. This adds direction to the calculation. For example, a storm moving at 20 kilometers per h east has a velocity of 20 kilometers per h east. Not just fast, but fast to the east. Pilots and meteorologists need velocity, not just speed, to navigate. In a 400-meter race, you might run 8 meters per second, but if you end where you started, your average velocity is 0. You can have high speed but 0 average velocity if you return to your starting point. Velocity's units are the same as speed, but always include direction. Average velocity is total displacement divided by total time. It tells us the average rate of change of position, direction included. Velocity gives a complete description of motion. It's essential for understanding real-world movement. Always ask, how fast and in which direction? What a journey! We've explored motion everywhere, from walking people to spinning planets. To describe motion, we need a reference point. Without it, motion is meaningless. We measured motion as distance, total path, scalar, and displacement, straight line vector. We compared uniform, steady, and non-uniform, changing motion, and saw how they look on graphs. We calculated speed, distance over time, scalar, and velocity, displacement over time, vector. These concepts are the foundation of physics and help us describe the world precisely. From snails to satellites, these principles let us analyze any movement. Here's a thought. Can an object have constant speed but changing velocity? If direction changes, so does velocity. Next time, we'll explore what happens when velocity changes, acceleration. Stay curious and get ready for the next adventure.